Looks good. So thanks to Moritz for setting the stage on optimization methods for non-smooth systems. And I'm very pleased that I now have the opportunity to go a little bit more in depth about one particular application that uses these methods. So the application we are going to investigate in the second half of the talk are assembly problems, which we want to solve by model-based methods. So if you have, for example, a model of this assembly problem where a clan type object has to be assembled onto a strut, we could compute a nominal motion which is just moving the object from A to B.
Or it's not oh, it's just the delay.
Okay. Yeah. So if some of the slides are not up to date, it might be a problem, but I'm going to continue now. Okay, so we have this nominal assembly motion. I can show it again. The object moves from A to B. There's no real contact interaction because there's no reason for the solver to use any contact interaction. If we execute this on a real robot, it usually will not work because the geometric positions and also the dynamical behavior on the real system is different to what we have in the simulation model. For this reason, we want to obtain a robust solution, which we do. These slides are also Zoom. So we want to obtain a robust solution for our problem, and we do it by considering multiple instances of the object. Each instance tracks a reference trajectory by an impedance law at a constant positional offset. If you would not have the constant positional offset, all instances of the object would collapse immediately to the reference through the impedance law. And we then optimize the reference trajectory in a way such that it brings all object instances to the goal position. And what we obtain is a robust reference that has the sliding behavior that then also results in a successful execution on the real system. And the nice property about this method is that it only depends on the initial position of the object, on the goal position defined by the user, and on the geometric model, and does not need any fine-tuning for a problem-specific assembly problem. And we can then also solve a more complicated task like this fan cover assembly, where we have to align two pins and snap in a clip at the end. And in the following, I will then now try to explain how one can solve such a challenging assembly problem by using optimization methods for non-smooth systems. So we essentially need three ingredients: differentiable collision detection, differentiable physics simulation, and then we can formulate a robust optimal control problem. So how to do differentiable collision detection? We consider a sign distance function, which takes in two polytopes that have 2 degrees of freedom, the position and the orientation, which we capture in the system configuration Q. And the sign distance is then a parametric linear program with parameters Q that solves for the smallest scaling factor by which the two polytopes have to be enlarged such that they touch in a common point P. And this formulation is very nice because it approximates the Euclidean distance closely, but it's only a linear program. So it's a simpler formulation than one would obtain if one tries to determine the exact Euclidean distance. The issue is now we want to use the sign distance function inside an optimal control problem. So we have to provide derivatives to the solver, but the sign distance function per se is not differentiable. Whenever the polytopes are in a configuration where two faces are parallel, there are multiple primal solutions to the linear program. And whenever the polytopes are in a configuration where two vertices touch, there are multiple dual solutions. And both cases result in a non-differentiable configuration for the sign distance function. So what we do, and I would claim this is one of the nicest approaches to obtain a smooth solution of a non-smooth value of coming out of an optimization problem, is using the smoothing implied by interior point methods. So an interior point method does not solve the exact KKT conditions of the distance linear program, but instead it solves a perturbed set. So for tau 0, one obtains the exact KKT conditions. For tau bigger than 0, the perturbed KKT conditions are perfectly smooth set of equations, which then yields a unique primal dual solution, which we can then use to evaluate the objective function of the linear program and use as a now smooth distance function, which is infinitely differentiable. If we think about it geometrically, we basically smooth our polytopes and they get shrunken. So it's very important for assembly problems that we decrease the size of the polytopes. We over-approximate the exact distance, because if you would increase the objects, assembly problem with tight clearances will then be an infeasible problem. Okay, and this is just as a kind of side note. So for contact, for physics simulation, one does not need only the sign distance, but also a contact normal, which is usually chosen as the gradient of the sign distance. So we need to provide the sign distance and the gradient to the numerical solver, and to enable IPO, for example, we also need to provide first and second order derivatives. And all of this can be done efficiently. That's kind of what I want to show here. And the point is, the main computational cost is for solving the smooth problem. The derivatives are not the bottleneck. They are quite cheap in comparison. Okay, so now we have differentiable collision detection, and we can formulate physics simulation equations. So the case for assembly problems we look at is one object is actuated, the other does not have any degrees of freedom, and both objects can consist of multiple convex polytopes. And then for each pair of convex polytopes, we can compute the smooth sign distance. And having all these smooth distances, we can formulate a time-stepping simulation method for contact physics, which is a standard formulation we use here, so I'm not going into it in depth. Essentially, in the time-stepping discretization, we again have a complementarity constraint between the object distances and the corresponding contact forces. And we smooth this complementarity constraint again by using Scholz's method, as Morris introduced, where the Scholz parameter here is called sigma. And in the end, we obtain equations where for a given state xk and a control force uk applied to the actuated object, we then can solve the equations to obtain the next state at the next time step. And we also obtain corresponding contact forces that bring us to this next state. The smooth differentiable physics simulation equations now depend on the two smoothing parameters sigma and tau, which smooths the collision detection. Okay, we could then use these equations to solve an optimal control problem for an open loop control sequence U, which would likely not help us to solve assembly tasks on the real system, because the dynamic behavior on the real system is different to what we have in simulation. So instead, we consider an impedance law, which is a state feedback law that is included in the optimal control problem. And basically now, if we have a reference trajectory, the control applied to what we call compliant trajectories, so the trajectories that also have physics simulation, the control input for these trajectories is computed based on the position of the reference trajectory. Okay, and then in the green box, the impedance law is a function of the reference state of the compliant state. We get a control force for the compliant state. Okay, and now we put all these building blocks from the previous slides together into one large optimal control problem. So we have multiple instances of the same object tracking the same reference trajectory. So the effective control input is, in this case, are the velocities of the reference trajectory, which determine uniquely the evolution of the reference. The impedance law then computes the control forces applied to the compliant scenarios of the object, which are simulated by using the differentiable physics simulation equations. Okay, and ideally we would like to solve this problem for very small segment tau, because then we're very close to the original non-smooth collision detection and physics simulation equations. But then it's quite hard for our numerical solver to find a solution, because we have a very non-convex, nonlinear problem. So the idea is to first use large tau and sigma, kind of similar to what Moritz showed with this homotopy of tightening this relaxation of the complementarity constraints, find an initial solution, and then make tau and sigma smaller, warm start the next instance of the optimal control problem by the previous solution. And doing this, we can get down to very small sigma and tau that then approximate the original non-smooth contact physics very accurately. And in the new solver CC-op, this is done more smartly by combining the interior point and these smoothing parameters jointly. Okay, and then so here I have the also have another software frameworks. I'm using Custodian IP-opt, and I'm trying to interface the stand distance function evaluation efficiently. So it's just kind of to state, okay, you can do this with nice software, you can do it efficiently. And now I want to show one more real-world experiment. So we again consider this clamp assembly problem. We have 30 instances of it. So on the horizontal axis, on the left side, there's no model uncertainty. And on the right side, we have a lot of model positional uncertainty. So the deviation of the object instances to the reference is 5 millimeters on the right and 0 on the left. And in between, it gets up to 5 millimeters. On the vertical axis, it's just different starting positions. We have 30 instances of this problem. We solve it to obtain 30 reference trajectories, which we can then execute on the real robot. We here kind of fine-tune the geometric positions on the real system such that we assume they match perfectly to the simulation, and then inject purposefully, again, 3 millimeter mismatch to being able to certify that our method really creates robustness. So if we then kind of check the result of the execution of our 30 instances on the real system with 3 millimeters of purposefully injected position mismatch, you kind of see, so the ideal behavior is that if you model 3 millimeters or more, we are successful. But of course, the dynamic behavior on the real system is still different to the simulation, so it works for all starting positions, but the fifth one, there we need to model even more uncertainty. But the idea is modeling more uncertainty makes you more robust. So here we repeated the experiments for different purposefully injected model reality mismatches. And in the middle plot, you can see if you model more positional uncertainty, you become more successful. On the right plot, you can see if you use more homotopy iterations, you become more successful. So the idea is more homotopy iterations, more accurate physics. And then on the left, both plots are combined. And then you can also think about interesting trade-offs. So you can say, I model more positional uncertainty, but solve my physics less accurately, or vice versa. Or you do both. You solve the physics very accurately, you do model a lot of uncertainty, and then you're very robust against model reality mismatches. Okay, so this brings me to the conclusion. So I hope I could convince you that I think there's great potential for model-based methods, model-based optimization methods on difficult manipulation problems, such as assembly tasks. And then kind of coming back also what Moritz explained to us. So this assembly problem is then a very non-convex, non-linear problem, but even in this case, derivatives enable us to solve it and to find solutions that also have an impact in the real world. And then finally, coming back to the big picture, mathematical programs with complementarity constraints are really the language of doing optimization of non-smooth systems. And they are a powerful tool to do it in a structured, disciplined way. And cool advances regarding solvers for these problems then also enable, again, solving more challenging applications. Okay, so this is the end of my talk. Thank you very much.